All right, on this video, we're going to talk about Stokes' theorem, which is used to generalize Green's theorem, something we talked about earlier, for circulation, and we'll talk about curl. When we use Green's theorem, we were talking about circulation around a closed curve in a plane, in a 2D plane. But now we're going to generalize this to three-dimensional surfaces. So on a previous video, we did introduce the idea of the curl vector for a vector field. And in order to define curl, we define this del, we usually call this just a vector made up of your three partial derivatives. And the curl of f of a vector field is defined to be del crossed with f. And what that does is it measures the circulation microscopically at any given point based on the vector field we're dealing with, the tendency for that vector field to cause rotation. Counterclockwise we'll define as positive rotation. However, it is a cross product, so it does, the curl of f itself is actually a vector that would be perpendicular to the plane. Well, yeah, it would be. Not necessarily. But anyhow, the length of that vector would sort of denote the strength of the rotation tendency induced by the vector field. So if you actually work out a general curl for a vector field f, if we define f to be m, n, and p, which we've done earlier, then del crossed with f, there's del, there's my field f, will give you this vector in general, which again, on a previous video, when we talked about the idea of a conservative vector field, if a vector field is conservative if the curl of f at every point is equal to 0. So, and then recall for a two-dimensional curve, when we use Green's theorem to find the circulation around a two-dimensional curve, this is what we were integrating. We were using the k component of curl because we were in the plane, we were in the xy plane. But now that we're going to be extending this to surfaces, our curl vector is going to always have this form, and these will not necessarily be 0 here. You may also recall how you can tell that a field is conservative is, again, the curl of f should be equal to the 0 vector, which means each of these parts should be equal to 0. And if they're equal to 0 and you set them equal to each other, this is the test you may be familiar with for determining if a vector field is conservative or not. So if the curl of f is equal to the 0 vector, then f is conservative. So what does Stokes' theorem say? Stokes' theorem says this: if we have a smooth oriented surface, again, oriented means we have to define which side we're talking about. There has to be two sides to your surface. A Mobius strip is a one-sided surface. All other surfaces, we usually will have two sides, so we need to be orienting ourselves which side of the surface we're talking about. And it has a smooth boundary curve, C. For counterclockwise rotation, that's what we defined as positive circulation around C. This is what we can now do. That line integral, this should be familiar, for calculating the circulation around C is equal to the surface integral of, this is the curl of f, dotted with n. We want to find out how much of that curl vector is moving in the direction of n, perpendicular to your surface. And we want to integrate that over the whole entire surface that is bounded by the curve C. And these two integrals are equal to each other. And we're going to see how that can be very, very useful. Now, why that works, it's actually kind of easy to see if you think about on your surface, let's pretend we're looking down on this surface here. Every single point at a microscopic level, we're calculating the curl, and the curl is going to measure the circulation around this microscopic point. If you think of each point next to each other as little tiny squares, you can see that the curl of this square here, right here, this is going down around the next adjacent square, this is going up. And because these 2 points are infinitesimally equal, close to each other, these should be equal in magnitude. They're going to cancel out. Same thing here and here. This one's going to the right, this one's going to the left. They're going to cancel out. So all of these squares, the curl, the circulation is going to cancel out next to each other, except what about a point that's right on the boundary? If I can't make it infinitesimally small, but if I had a small point there, yes, I will get some cancellation on this side, and this side, but there's nothing to cancel this. So all of my points right on the boundary, the circulation will not cancel. And so by adding up all of the circulation around each of these microscopic points here, even though these are all going to cancel, because the ones on the outside are not going to cancel, that's the equivalent to finding just the circulation around my curve. And a cool result of this, and we're going to take advantage of this going forward, is any 2 surfaces with the same boundary curve, they must have the same curl surface integral. If you think about it, right? If I integrate, this is an upside down cone, this is an upside down paraboloid, top half a hemisphere. If they all have the same boundary curve, and you add up the circulation at all the points on the surfaces, like we said, they're all going to cancel except for the ones that go around the boundary curve. And since they have the same boundary curve, the surface integral for curl for all 3 of these should come out to be the same, which is the circulation around the curve C. So basically what Stokes' theorem says is this: if we want to find the circulation, I'll define this, sometimes called the flux of the curl of a surface around a curve C. So if we want to do the line integral that we're used to doing around some boundary curve C, we can either do that line integral, or we can do the surface integral where we're adding up, again, this is the curl of F dotted with N. And that's part of the reason we call it the flux of the curl. We're adding up the curl, but we're dotting it with N, which is the vector that's perpendicular to the surface. It's just a measure of the curl there. So, and if you recall, when you're measuring stuff that it's going out away from the surface, we usually call that flux. So it's the flux of the curl is another way to describe this double integral here. And so we can calculate the circulation around the boundary curve either way. And so depending on which formula we use for d sigma, the surface area differential, we can get slightly different formulas. We've seen this before when on the video with surface integrals. If we use a parameterization for d sigma, then this double integral curl of f dotted with n d sigma. Remember, for parameterization, you would have r sub u crossed with r sub v. You'd have 2 parameters, divide by the magnitude. That would be your n vector, right? That would be your normal vector. And then d sigma is just the magnitude of ru crossed rv. Those are going to cancel out, and we're going to be left with just this double integral. Likewise, remember, we have another formula for d sigma using the gradient vector, and in which case our surface integral will have this form. I use n as the gradient divided by its magnitude. Use this for d sigma, the gradient vector cancels out, and we're left with this formula for our surface integral for flux of the curl. And similar to when we've done these before, which formula should you use? Many times it doesn't really matter. There are times when maybe one is maybe better than the other, but they should give you the same value. So let's see one. Example. We want to find the flux of the curl for this vector field across the surface of the cone z equals 5 minus the square root of x squared plus y squared. That looks like this. Above the xy plane in the direction of outward unit normal n. When you read the directions on these, sometimes it's a little confusing. What are they talking about here? This gets back to the orientation here, and it also has to do with the flux of the curl. If we do the surface integral of this cone, adding up the curl vector, typically what we'd want to do is use that to evaluate the circulation around this boundary, and positive circulation is counterclockwise. So the reason they said in the direction of the outward unit normal n, if I can picture a vector like that, is because if I have a vector going away there, then that's going to be true for a circulation that is rotating counterclockwise around that vector. And remember, they all cancel out if I start putting my little squares, but if I imagine right down here evaluating a circulation there, see at the bottom, it's going to be going in the same direction. It's going to be going in the counterclockwise direction. So if I had a vector going inward, it would be the opposite. It would be going clockwise. Okay, back to the problem. So they're actually asking us to find the flux of the curl, but because that should be equal to the circulation around the boundary curve, one way to do this is to just evaluate the line integral of f dotted with dr around this circle. So to find that circle, it is the intersection of the cone with the xy plane. In other words, setting z equal to 0. And if you solve that, you just get a circle x squared plus y squared equals 25, circle with a radius of 5. I'm going to do this as this should be review. So if I want to do the line integral, I can parameterize my circle. R of t is 5 cosine t, 5 sine t. I need dr, just the derivatives. And on r of t, my vector field, it was given up at the top, x minus y, y minus z, z minus x. So all I've done here is, if this is x and this is y, x minus y, y minus z, and z minus x gives me that for f. And if you do f dotted with dr, try that yourselves, do the dot product of this. Everybody cancels out except for 25 sine squared t. So then what you'd want to do is do this integral here. This might be a good chance to pause the video, make sure you can integrate that. Give it a go. And if you do that, use the identity for sine squared t, integrate, you should get an answer of 25 pi. Now, using Stokes' theorem, I could also just do the integral directly. The problem asked me to find the flux of the curl of our vector field. So it kind of implied they actually wanted us to do a double integral. They wanted us to integrate over the surface. So now we're going to do it with the double integral, integrating the curl of f dotted with n on the surface. And just made a note here. Remember, we had two options for d sigma. I'm going to do this one by parameterizing the surface rather than doing the gradient method. And maybe part of my motivation is, if you remember doing the gradient, you would have to take the derivative of this function. You would move the square root of x squared plus y squared over to the other side and set this equal to 0. And that derivative is going to be kind of messy. So parameterization might be better. So we're going to parameterize this using r and theta for the cone. X is r cosine theta, y is r sine theta. And remember that z is 5 minus the square root of x squared minus y squared, which means z is really 5 minus r. So then we have to calculate the cross product. Take your partial derivatives, do your cross product. You should get this right here. The curl of f is del crossed with f. So we're going to do the cross product. There's del crossed with f. I left it in terms of x, y, and z. And actually, if you do that cross product, you should get 1, 1, 1, which is kind of nice. Then I'm going to evaluate the curl of f, which is this vector. Remember, I just showed it again that when you do n is this vector, d sigma is this vector, but the magnitudes cross out. So you really just have to do the curl of f dotted with r sub r across r sub theta. By the way, back up to here. We were talking about earlier on when we did it the first way, why we want, if problem said to do the surface integral with n pointing outward. And as you know, when you do a cross product, you could get, depending on which way you do the cross product, you could either get a vector that's perpendicular going outward from the surface or going inward. So how did I know which direction to do the cross product so that I was producing an outward unit normal n? So imagine this cone here, level curves here are circles, and we're parameterizing in terms of r and theta. So if I take a random point here, if r sub r means I'm moving in the direction of increasing r, right? So which direction would that be on the surface? You'd be going down the cone here. Whereas if I was changing theta in a positive way, I'd be going around the circle, so I'd be going around this way. Convince yourself that if you do the cross product with the right-hand rule, that r sub r crossed with r sub theta would give you a vector going outward. If I did it the other way around, I would get a vector going inward by the right-hand rule. So that is something that is a little subtlety when you're doing using Stokes' theorem with a parameterized surface with two variables. You do have to think about what order you should do the cross product. So we have another example of that coming up. Anyhow, back to the double integral. Do the dot product, end up with this. I factored out an r. I integrated with respect to r first and then theta. Again, maybe pause the video, make sure you can run through this work. But as expected, we got the same answer, 25 pi, which is the same answer we got when we did it using the line integral. Now, what I want to show you next is actually, this is what's really cool about Stokes' theorem, is that idea. So we're going to do the same problem with that same vector field. But remember what we said was that is any surface that has the same boundary curve should give you the same value for the flux of the curl. We just did a double integral, surface integral for a cone that had this circle of radius 5 as its boundary curve. But if any surface is going to give me the same value, why not? The simplest surface I would use is, why don't I just use this flat disk? X squared plus y squared is less than or equal to 25, with z being 0. And let's see what happens. Remember, my formula here is I want to integrate over the surface the curl of f, which is del crossed with f, dotted with n d sigma. We already found that the curl of f, we just did that on the previous page, was 1, 1, 1. But n is a normal vector to the surface, and I don't need any formula to find the normal vector here. A normal vector to this surface right here is just k hat. It's in the xy plane, or in other words, 0, 0, 1. So if I do dot that with 0, 0, 1, d sigma, or dA, I guess, what does that give me? That gives me the double integral over my region now, over the area. If I dot that product, it's just going to give me 1. And this double integral just corresponds to the area of this region it's a circle of radius 5, so that should come out to be pi times r squared, 25 pi, which is the same answer we got. So very, very cool. Could you, on a test, if you knew this, rather than doing this double integral over the cone, which gave us kind of a messy integral, knowing that I'm going to get the same answer if I just use as my surface this flat disk here, it's a much simpler integral. That's something to maybe ask, because it is true and it's going to be a lot easier, and it does show that you understand what Stokes' theorem is. I'm sure there might be some professors that say, yes, I know that's true, but I would like you to do this integral that we just did over the cone as well. That could be a conversation you have with your professor. Okay, one more example here. And other than that, just the last example, that if you use the flat disk, it became easier to do the surface integral. When we looked at the cone, integrating the cone surface versus just doing the line integral, it seemed a lot easier to just do the line integral, since that was equal to the flux of the curl. But that's not always the case, and that's the whole point of Stokes' theorem, is you have options. So here's an example. We want to find the circulation produced by this vector field around the curve C that is bounded by the triangle cut from the plane x plus y plus z equals 1 in the first octant. And there's this idea of orientation. On the previous example, the orientation they gave us is they said, find the flux of the curl for the direction of outward unit normal, a vector pointing outward. Another way to orient ourselves and decide how do we want the circulation to be calculated is counterclockwise. That's typical as viewed from above. If you were looking from above at the top of this and looking down at this triangle, counterclockwise would be in this direction as opposed to the other direction. All right, so now we have some orientation. Now, why, in this case, I wouldn't want to do the line integral, because there's 3 curves, right? Curve 1, curve 2, curve 3. If I was to do it with a line integral, I'd have to do 3 integrals. So now what I want to do is use the idea that the surface integral over this flat surface, this triangular surface right here, is going to give me the same value, right? All of those little circulation vectors next to each other are going to cancel out, except for the ones that are right on the boundary, right? So we're going to parameterize. The simplest way it seems to parameterize this plane is to just let x be x, y be y, and z, if you solve for z, is going to be 1 minus x minus y. Now, here's where that subtlety comes in, because I have 2 ways I could do r sub x cross r sub y, or r sub y crossed with r sub x. How do I know which way to do that? Because I want to calculate circulation counterclockwise as opposed to clockwise. So go back to this idea that if you're at a point here, what does r sub x mean? R sub x, if you were at this point, you're going to move your x value, you're going to change your x value, and you're on the surface, you'd be moving kind of this way, right, along the x-axis. So there's r sub x. R sub y would be going in the y direction on the surface, something like this. So which order would you do a cross product to produce a vector that's going outward like this? Because that's essentially going to give you circulation that's going this way, which we could see would be in the correct direction. And hopefully you can see that would be r sub x crossed with r sub y. I'd want to pull r sub x into r sub y by the right-hand rule. That would produce a normal vector that's pointing outward. So that's why I chose this here. So maybe pause the video. You might want to see if you can work out this double integral. Here's r sub x, here's r sub y. If you do the cross product, you should get the vector 1, 1, 1. For my curl of f, del crossed with f, gives me this value. I want to keep my integral in terms of x and y. So remember that on the surface, z was equal to 1 minus x minus y. So that means I could replace z with, well, how about this? If I go z minus 1, then that's just like subtracting the 1 over here. That would be equal to negative x minus y. And so then I'm going to do my double integral. Curl dotted with rx cross r sub y gives me this to integrate over the area. Okay, now, yeah, how do I get the area? Remember that the area would be you're integrating in the xy plane would be this triangle here. So if I drew a little mini version of that in the xy plane, this was intersecting the y-axis at 1, the x-axis at 1. So this equation is just y equals 1 minus x. So y varies from 1 minus x to 0 as long as x is between 0 to 1. And if you work out that integral, but lots of boring work, you end up with negative 5/6. You may have noticed when we did the parameterization and we did the cross product, r sub x crossed with r sub y to get a normal vector, we got 1, 1, 1. You may have noticed that's actually the gradient of our surface. X plus y plus z equals 1 gives you a gradient of 1. Because I mentioned the other way formula for d sigma you could use is the gradient version. So that's what I'm doing right here. The gradient is 1, 1, 1 as well. And remember what happens, you would then have to divide by the gradient dotted with p, but in the xy plane, p would just be k hat. So if you dot the gradient with p, you're just going to get 1. So the denominator becomes 1. So it really just boils down to the curl of f, which we already worked out, dotted with the gradient of f, integrating that over the area, and that gives me the exact same integral we just did, which is negative 5/6. Okay, I'm going to make another video after this where we do some more examples using Stokes' theorem and again, deciding whether we want to do the line integral to evaluate something or do the surface integral. I think lots of examples would be helpful here, so stay tuned.